If I find my way home, yeah. Wouldn't it be crazy? But you still amaze me. If I find my way home,
Welcome back, everybody. Today we're going to continue on with mapping, and we're going to learn how to actually measure latitude and longitude. While you're watching, make sure you take notes in your Topic 3 note packets, starting on page 6. So how do we actually find positions in the world and navigate from one place to another? Well, today it's easy. Google Earth will show you your exact latitude and longitude. iPhones and other mobile devices have a GPS built in, and Siri will tell you exactly how to get to wherever you want to go.
In 1 kilometer,
Now, I know it might be hard for some of you to believe, but there was a time before these electronic devices existed, and people had to figure out things like this all on their own. Finding your way around the world was a lot harder back then. So how'd they do it? Well, that's what we're going to see today. Today we can use latitude and longitude to find our position on the Earth. But that's not a new system. We've been using it for a long time. But before we could actually look it up at Google Earth or even on a map, someone had to invent the system. So let's start with latitude. Remember, latitude is a measurement of our position north or south of the equator. Well, long ago, when people would travel long distances on Earth, they didn't have maps to follow, but they did have the stars. And they figured out that one star in particular will tell you how far north or south you've gone. And that star is called Polaris, also called the North Star. Now, if you remember from the last video, Polaris will appear to rise as you go north and sink as you go south. Well, it just so happens that if you actually measure the angle of Polaris up from the horizon, you get your latitude. Now, the horizon is not really an actual place. It's simply the farthest point that you can see to on Earth's surface. So when ships were out at sea, at night they would find the star Polaris. It's pretty easy to find, actually. It's the last star in the handle of the Little Dipper. Then they would measure the angle, or altitude, from the horizon up to the star Polaris. Whatever angle they got was their latitude. So in this example, the angle of Polaris is 52 degrees. Therefore, the latitude of this ship would have to be 52 degrees north. Remember, you can't see Polaris south of the equator, so it has to be north. Now, why does this work? Well, it really has to do with the geometry involved, but it is this simple. Whatever the angle of Polaris is the latitude in the north. Okay, so let's take a look at page 6 in your notes. Write this down. The altitude of Polaris means the angle measured from the horizon up to the star Polaris. And yes, I would like you to draw this little guy measuring the angle from the horizon up to Polaris. So here's how this works. Let's say you're at the equator and you find the star Polaris in the sky. Notice in this diagram, Polaris is right on the horizon. So if you're trying to measure the angle up from the horizon, but it's on the horizon, the angle's 0. And guess what the latitude is at the equator? 0 degrees. Now let's say you go north from the equator and you wind up in New Orleans, Louisiana. You find the star Polaris again and you measure its angle up from the horizon. Now you get 30 degrees. The latitude in New Orleans, therefore, is 30 degrees north. If you keep going north, as far north as you can go, you'll wind up at the North Pole. There you will see Polaris is straight above you, 90 degrees up from the horizon, and the latitude at the North Pole then is 90 degrees north. So that's how you measure latitude. Longitude, on the other hand, is a little trickier. There is no star that we can measure the angle of that tells us longitude. Instead, it's based on Earth's rotation. The key to figuring out longitude is knowing Earth's rotational rate. So we'll do a little math here. Like any round object, the Earth has 360 degrees going all the way around, and it takes 24 hours for the Earth to spin once through all 360 degrees. So if we do a little math, 360 divided by 24, you'll get the Earth's rate of rotation, 15 degrees per hour. So if we know how many hours of time separate two places, we can figure out how many degrees of longitude would separate them as well. In order to make this work, we need a starting point for longitude, and we need to always know the time at that starting point. Now in this case, our starting point is called the prime meridian, and the time there is called Greenwich Mean Time. We also need to know the time at another location. We call that the local time. So let's say that Greenwich Mean Time is 12 noon. The local time over here is 10 a.m. So first we need to find the time difference. So you subtract them and you'll get 2 hours. Multiply that by 15 degrees per hour, the Earth's rate of rotation, and we'll get our longitude. So 15 times 2 gives you 30. And since this location is west of the prime meridian, that makes our longitude 30 degrees west. Here's another example. Let's say it's still 12 noon at the prime meridian, but over in this location in the east, it's now 7 p.m. The time difference is now 7 hours. So we multiply 15 degrees per hour by 7 hours, and we get our longitude, 105 degrees. And since this place is now in the east, that's what we label our longitude with, 105 degrees east. Okay, so let's go back to our notes. The procedure on finding longitude is already written out for you. You're welcome. What I would like you to do to finish these notes is to find the longitude of the 2 points labeled there, B and D. Use the prime meridian time of 12 noon and the local times that are listed there.
If I find my way home, yeah. Hey, wouldn't it be crazy? Oh, but you still amaze